All right, just a simple introduction here to relative motion. This starts in your packet. I think it's on 250 perhaps. I'm not entirely sure. Let's see here. Yeah, 250. So let's look at an airplane that's flying, and let's have a fixed point on the ground there, the reference point on the left, and let's look at the motion of the tip of this propeller on the airplane with respect to this reference point back here. All right, now that's going to be a pretty complex motion to describe, so the way to handle that is to break it down into simpler steps. So what I would do is I would find the motion of A with respect to the reference point is first I would look at the motion of B, which is a point in the middle of the propeller. That's going to have the same motion as the overall plane, and that would be a translation, some sort of straight line or perhaps simply curved motion. So I would track that first, and then I would look at how A moves about B, the motion of A with respect to B. That would be a rotation. Regardless of where the plane goes, A is always rotating about B. And then I would combine those two motions together. So if I were to do that mathematically for the velocity, what I would say here is the velocity of point A is equal to the velocity of B, which kind of represents the motion of the airplane. It's the center of the propeller there, plus the velocity of A with respect to B. That's how I would read that last term. And that would be a simple circular rotation there. And if I combine those two things together, I'll get the velocity of A. All right. Now, we could look at this also kind of, this type of relationship holds for position, velocity, and acceleration. It's probably simplest to see it with position. Okay, I can define the location of B with a simple vector with respect to the origin. That would be the position of B. In this case, it's 5, 3, okay, over here. Now, I could also, if I wanted to, put a coordinate system up here at A, and then figure out where it is with respect to my original origin over here. And let's say that's at 3, 4, so 3, 4. So x is 3, y is 4. To get to B, then, I'd go over 2 and down 1. Okay, that's how I would get from this new coordinate system to B. So to get my original coordinate of B, the position of B, which is 5, 3, I could take the location. So there's my 5, 3. I can take the location then of this new coordinate system and then add in how to get from it to B. So 3 plus 2 will get me 5, and 4 minus 1 will get me 3. So the way I would express that then is the position of B is the position of A, which is that new coordinate system, plus the position of B with respect to A. That's how I would express that. Now, when we set these equations up, we want to be sure we have them set up properly. The way I would do that would be to look at the subscripts. So what I want here is B on the left. That's the subscript over here, that on the left of the equation. That's going to equal the subscript of the first term. And then I think of working with fractions times the subscript of the second term. So if I just work with the subscripts, the way I can tell I've got this set up properly is just do a little bit of multiplication here. B is equal to A times B over A. The A's will cancel, so B equals B. So that's set up properly. Okay. Now, I started with position relationships. I can take a time derivative and from there get to velocity relationships. So I can say the velocity of B is the velocity of A plus the velocity of B with respect to A. And I can take a second time derivative, and I can get the acceleration of B is the acceleration of A plus the acceleration of A with, of B with respect to A. Okay. So these relationships hold for position, velocity, and acceleration. All right. So how about having a look at that equation there? Vm equals Vp plus Vm with respect to P. And look at the two diagrams and see if you can figure out which diagram represents the equation. Is it the one on the left or the one on the right? Which diagram is set up properly to represent that equation? All right, now the answer is the one on the right. And the reason is you got Vm, which is I've got in green there. And I'll outline it a little bit right there. That just goes to the right. That's over here on this side of the equation. And then what that equals is P going up, and then M with respect to P going down and to the right. So if I take the two blue vectors that I'm highlighting here right now, I know I'm kind of running out of space, but those are big vectors, but there you go, and add them together, I get the same path as below. And what's happening there is the vectors that are added together are put head to tail. That's how you add vectors together. So VP and VM with respect to P are put head to tail. This, on the left-hand side, P and M with respect to P are not put head to tail. So they're not, in the diagram, they're not added together as the equation shows. So the diagram that represents this equation is the one on the right. Okay, so that's just a little introduction. We'll kind of carry on in the next video with more of this.